Hi, in this mini lecture I will introduce JK and T-type latches and flip-flops as a 1-bit memory. You know already SR and D-type flip-flops or latches, and let's recall what is the difference between the latch and the flip-flops. The difference is in triggering conditions, or condition which allows the memory to change its value. In the case of latches, you've got two possible cases when the latch can change its value, when there is a 1 on CK on clock input or 0, but not both, either 1 or 0. So you've got two kinds of latches, and similarly you've got two kinds of flip-flops. The ones which are triggered can be changed, their values can be changed on positive edge, or alternatively on negative edge, but also not two at the same time. So you've got also two types of flip-flops, positive edge triggered and negative edge triggered ones. So let's wipe these out and let's start describing what the JK operation is. So similarly to SR, you've got two inputs, JK, which corresponds to SR. J is the set input, R is the K, reset is K. So similarly, Q is in front of J, not Q in front of K. We've got two outputs and of course CK input. And the first way is to describe it using state transition table in the shortened form, having only two JK signals, 0, 0, 0, 1, 1, 0, and 1, 1, and the next state after clock. Okay, you know that this +1 means the after clock. So after having all the possible triggering conditions. So we are sure that independently of the triggering condition, this element 1-bit memory could change its state. So these three rows are exactly the same, and in the case of SR, so then don't memorize the two tables, try to do it only once. So 0, 0 means don't change anything, so the next state is the same as the current state. 0, 1 with kasuika in Polish, and it is a reset input, so you must put 0 here, and this is the set input. J is the set input, so 1 is the new value of the memory. And in the case of 1, 1, which is not the load in the case of SR, here for JK, you've got the inversion of the content of the memory. So if you have 1, you will get 0 and the opposite. And it is called invert, this operation, invert or toggle. And this similarly as in the case memory. So don't change command. It is a reset command. It is a set command. Okay, and in a graphical form, it is a state transition diagram. Is also similar to SR, having additional case 1, 1 on JK. So 0, 1 are the states, two possible states of the memory content. The first row gives you a recipe how to do what to expect. If you put 0, 0, you expect no change. So no change means you stay in the same. You know, the current position and the next position is the same. For 0, 0, JK. 0, 0. Second row, reset. Independently what state you are in, the next will be 0, reset. The next will be 0. So if you are in 0, the next will be 0, and if you are in 0, nothing will change. You stay with the same state. The third row, set. Set means 1 on the memory. output. So if you are in state 0, you go to state 1. If you are already in 1, you stay in the same state. And the new, something new, is 1, 1. 1, 1 means toggle, so if you are in 1, you get 0, and if you are in 0, you get 1. So you change the state for 1, 1. This is new comparing to SR. And what about the STE equation? STE, the last possible way of describing latches and flip-flops is to deliver equation for Q of t plus 1. Okay. Let's put here JK and here the current state, and your task is to deliver the equation for the next state after clock. You are using Carnot map to have it in the minimized form. 0, 1 here, and you simply copy from this table. If you have a JK 0, 0, which is this first column, you simply have the same state as Qt. So 0, 1, the same states. Okay, Qt is 0, you get 0. Qt is 1, you get 1. Okay, so for 0, 1 in the second row is 0. This is the third, the last row. So you must invert Q of t. So 0 gives you 1 and 1 gives you 0. It is a toggle. And set is the last one. It is simply 1, 1. How to minimize it? You've got two groups. The first one and the second is here. And the equation is, from the first group you'll get, you have j times not q, j times not q of t, and plus from the second group, not k times q of t, not k times q of t. And that's all as far as JK flip-flop or latch is concerned. For latches and flip-flops, the description, this kind of description is the same. The difference is only in when you draw the timings, when these changes occur, when, not how, what is the change, what kind of change you expect, but when it is different conditions. So we'll be discussing this problem in the future mini lectures. So let's switch to T-type flip-flop, T-type, or simply T flip-flop, or T-type flip-flop or latch. And it is similarly to D-type. It has a single input, of course, apart from CK input and Q and not Q outputs as usual. And the STT table, shortened one, is a very compact. You've got only a single input variable, and on the output you've got the next state, and you must use Q of t as a current state. So it is like toggle. Its name is toggle, comes from toggle, and it toggles when it has 1. Similarly in JK for 1, 1. So it now will be not Q of t, toggle state. If you have 1, you will get 0 and the opposite. And for 0 on t, don't change anything. It is a memory. Okay, so there are two commands corresponding to the particular value of input line on the input line. So this is don't change anything, don't change state. And this is toggle. Invert. And the state transition diagram, STD, is the following: two state values, 0, 1 for Q, this signal. If you have a t equal to 0, you'll get the same. So you've got the self arrows, the closed ones. So 0, a single bit is here because you've got only a single input. So, and the second row gives you the recipe what to expect it if you have 1. You expect the change of the memory content depending in what state you are, what's the content, the current content. The next will be the inversion of the current. And the last one is to deliver the Q of t plus 1. It is simply XOR of Q of t and t. How to find it? You can expand, but it is better to expand this table. It is a shortened version, and the full version is when you have Q of t on the left hand side as well as t, and on the right hand side Q of t plus 1. 0, 0, 0, 1, sorry, 0, 0, 0, 1, 1, 0, and 1, 1. And you know that if you've got 0 on t, the same state you expect to have after clock, but if you have 1, the inversion, you expect the inversion. And this is the truth table for XOR, I hope, for XOR gate of two variables, of two inputs. You've got this pattern, it's XOR pattern, that's why I have put this symbol here. So it is a state transition equation, and these are independent of the type of triggering. The same description for flip-flops and latches, and the difference is, as I said, in timings. The timings will be the subject of the following mini lecture. Thank you very much.